Good afternoon, everyone. I am here to start the practice problem session for our last module, which was about the gas laws. Okay, so the you have learned. Let me um start with some background. So you have started the learn the Boyle's law, and law. The Boyle's law says we okay. So it is indirectly proportional to the pressure. The pressure is indirectly proportional to the volume, inversely proportional to the volume, right? And Charles law, so it describes the relationship between the volume and the temperature. And the Gay-Lussac law, and it describes the relationship between the volume and the amount, the volume and between the volume and the moles. And then the combined gas law equation, it combines all these three and found an equation P1 V1 over T1 equals P2 V2 over T2. Okay, then you learn the ideal gas law equation, which is PV equals nRT. So then we can reorganize this the ideal gas law equation to solve or work with the densities and the um, amounts. Okay, and so what else? The Dalton's partial pressure law. So P in pressure of individual gas equals the pressure of total multiplied by the the chi, that's the mole fraction. Okay, and then okay, this is then we are going to talk about the van der Waals equation, like the uh, we can apply the ideal gas law equation for only ideal gases, the gases which behave as an ideal gas. But simply you're going to use the ideal gas law equation, but then we're going to talk about the um, real gas law equation. There we introduce the correction factors for the volume and the pressure, and then the kinetic molecular theory. Okay, so those are the things that we are going to we you have learned and the covered under the module 8. Okay, so let's start the first question. Actually, this is related. This has been maybe you have covered or related in the with the module 1. This is a conversion question. Gas pressure is measured as 23.7 inches mercury. And what is the pressure in ATM? So for your final exam, as well, you will be given an equation sheet which will have all the values for the constants and other the relevant um, values for the other constants that you are going to use to solve those problems. Okay, so we'll start with the 23.7 and 1 inch, okay, equals to 2.54 centimeters. But still we don't have the uh, direct relationship between the centimeters and the mercury. Then we'll change that into millimeters. 10 millimeters equals to 1 centimeter. And okay, so then we know 760 millimeters equals to 1 atm. So that's how we have to go through two other steps to build a relationship between the inches and the ATM pressures. Okay, so here we'll start with 23.7 inches mercury, and then we get the relationship between the inches and the centimeters. Then the inches to inches cancel out, and then the centimeters to centimeters cancel out. We'll get the uh, relationship between the centimeters and the millimeters, and then we'll get the relationship between the millimeters and the ATM. Okay, so you'll get the answer in the ATMs. So it is 0.792 ATM. So always you need to follow the significant rule, the rules. Okay, so here we are given with a value which has three significant figures, so we'll give the final answer with three significant figures. Questions? Okay, then I'll move to the next one. At 35.0 degrees of Celsius, a sample of a fixed amount of ideal gas occupies 420 point milliliters at a pressure of 1.25 atm. What will the volume be at a pressure of 0.900 atm? Note the temperature remains constant. Okay, this is something that you're going to practice or start doing that. For all the gas law equation, the temperatures must be applied in Kelvin. In general chemistry too, you will do lots of examples, lots of calculations using chemical equilibrium, chemical kinetics, and thermodynamics. There, in everything, you have to, starting from this module, you should apply the temperature in Kelvin. Okay, keep that in mind. So we have talked about the relation, the conversion from these degrees of Celsius into Kelvin in the module 1. Okay, so if you have forgotten these things, please go back and review your uh, knowledge, or please refresh your knowledge on these things, because next week you are going to take the final exam. Right. Okay, so in this question, there is lots of things. So this is what I would do. I would draw a small picture. Okay, this is the condition 1, this is the condition 2. So now I add the parameters for the sample 1, and this is the sample 2. Okay, the condition 1 and the condition 2. At the initial conditions, the temperature is 35, okay, 0 degrees of Celsius, and I was given the volume 420 milliliters. The and the pressure is 1.25 atm. Okay, and then I move to the condition 2. So what does it say? What will be the volume? Oh, I don't know the volume. I should find the volume. But what would be the pressure? The new pressure is 0.900 atm. And what does it say about the temperature? Temperature would be the same, so it would be 35 degrees of Celsius. Okay. When you illustrated your data, or when you make a picture, put this data into a picture, you will clearly see what or which parameter is missing in this picture. Okay, so now the temperature is kept constant. So you can use either P1 V1 over the combined gas law equation, or the Boyle's law equation. Boyle's law equation, what do you get? P1 V1 equals P2 V2. So this is at constant, at the same temperature and the same amount. Okay. Um, or you can use the P1 V1 over T1 equals P2 V2 over T2. But the temperatures are equal, so basically we can use the Boyle's law equation. Okay, so let me add P1 V1 equals P2 V2. Right. Now I'm going to solve for V2. So let's reorganize this equation. P1 V1 over P2 equals V2. Okay. So now you just have to plug the values. What is P1? Okay. Now here it's easy. 1.25 atm. Or let's plug it with the unit. V1 420 point. Okay, look here, you'll see that the dot. So that means this number has three significant figures, milliliters. And what is P2? Yes, 0.900 atm. Okay, now I hope you can find the answer for this. Can you all can use your calculators and try to get the answer now.
So we don't have to change the volume to liters in this equation, only if it asks for it in liters.
That's right. So you otherwise, if the question didn't ask the volume in a certain unit, you can plug the volume in milliliters. Yeah, that's right. That's a good question. Oh, the look, the next thing, the both pressures and the volumes in the same type of unit. It cannot be in two different units. That's the other thing. Okay, it can be in atms, or it can be in mercury millimeters, or it can be in pascals, but doesn't matter. The both sides should have the same type of units for the volumes and the pressures, volumes and pressures. But when you are going to work with temperature, always the temperature must be converted to Kelvin. Good question. So what did you get for the answer? I got the answer as 583.33. Is that correct? Did I follow the significant figures? No. So the V2 equal 583 milliliters. That's the correct answer. Questions?
I have a question about like significant figures. Like if say you have a problem like this and you're given the temperature in three significant figures, but the pressure in four significant figures, do you always use
Pressure, where the pressure is given with four significant figures.
it's not. I'm just saying like
Okay.
in a made up scenario, you have
Okay.
two
Hmm.
different significant figures. Would you just use the lesser value? So like
Yes.
okay.
Yes. Please review your module one. It's going to be different. With the subtraction and additions, you will stay with the number of decimal places. but with the multiplication and the divisions, you will stay with the least number of significant figures. There are different rules. Any other questions? Okay, then I'll move to the next one. So this is going to be, I'm going to do the I'll do only the description because I just want to save the time for the questions on at the end, like after about 20 or 18. Okay, here is another question. Anesthetic gas is normally given to a patient when the room temperature is 20.0 degrees and the patient's body temperature is 37.0 degrees of Celsius. What would this temperature change do to 1.60 liters of gas if the pressure and mass stay the same? Okay, so this is again you can use. Okay, so if you draw a picture, condition 1, condition 2, at 20 degrees of Celsius, the volume is 1.60 and it as at 37 degrees of Celsius, what would be the new volume? Okay, so you can again, so it says the temperature and the mass are constant. So we have the same temperature for both cases. So here you basically look at the relationship between the volume and the temperature. So you'll use the Charles law. V1 over T1 equals V2 over T2, uh, right? And uh, temperatures has to be applied in Kelvin temperatures. So this and this has to be changed to Kelvin before you apply it into the equation. That's how. So then only thing is missing is the V2. So you rearrange this equation V1 T2 over T1 equals the V2. Questions? How do you change the temperature degrees of Celsius to Kelvin? Yes, you will add to the temperature in degrees of Celsius. You add 273.15 Kelvin. Okay, then you will get the, you can convert the temperature in degrees of Celsius to Kelvin. Questions? Okay, then I'll move to the next question. Okay, let me, if you, I've seen 2 students have joined with this session. You guys can do the problem and let me know if you uh, experience any difficulty or any problem. I'll give you 1 minute to get the answer for this question. Let me know if there is any trouble or if anything that you are concerned. Okay, since
For
I,
the
yeah,
for the volume, we do subtract, right?
excuse me.
For the temperature, we subtract that 37 from 20.
No, no, no. You don't subtract anything. That's the uh, second temperature. Okay, so then you'll
Okay.
add the 37 degrees, 37.0 to 273.15. Okay, to get the T2. Any other questions? Okay, let me, if there is no, there are no other questions, so I'll move to the next problem. So what did you get? Like the, let me do it, V1. That's the 1.60 liters times T2. What is 37 plus 273? It would be 300, right?
It's 310. 310.
Oh, 310, sorry. 310.1, because 37.0 has only one decimal place and this other one has two decimal places, but we have to stay with one. Okay, and divide by the T1, it is 293.1, right? So you can get the answer for, so this is in Kelvin, this is in Kelvin, Kelvin to Kelvin cancel out, and you will get answer in liters. Okay, right. Next one. Now again, a sample of 320 milliliters of nitrogen gas is at the pressure of 735 torr. Now we are given the pressure in torr and a temperature of 15 degrees of Celsius. What is the temperature of the sample at a pressure of 1250 torr? Okay. So condition 1, condition 2, condition 1, the volume is 320 point milliliters. So that means it has three significant figures. Pressure is 735 torr and a temperature of 15 15 degrees of Celsius, and the temperature of the sample at a pressure of, what is the temperature of the sample at the pressure of 1250 torr? Okay. Does it say anything about the volume? No. So what should we assume? Yes, if it doesn't say anything about the volume, then you need to assume that volume is kept constant. Right. So volume is a constant. We have the same volume. And we are looking for the new temperature. Right. So you can get the combined gas law equation. Okay. Or the P1 V1 over T1 equals P2 V2 over T2. So V1 and V2 are equal. So we'll get P1 over T1 equals P2 over T2. We are looking for the T2. Okay, so let's reorganize this equation. T2 equals P2 divided by T1 and P1. Right. What is the other thing? We should change these temperatures into Kelvin. Okay, that's the important thing. So P2 Can you please mute your microphone if you are not, if you want to ask me a question, just unmute your microphone. Other than, please keep mute your microphone. So P2 is 1250 to T1. So we should change these degrees of Celsius to Kelvin. 15 to 273.15. Okay, so it will be 8, 8 and 2 Kelvin times the P1, 735 to. Okay, so I hope you will be able to solve this equation and find the answer in I did something wrong. Yeah. Here. Let me get the eraser. I'm looking for the here. The T1 should go up there. Okay. $288, right? Yeah. So toe to toe cancel out and you will get the answer in Kelvin. Questions?
I have a question. Could you have also used the ideal gas equation, the PV equals to nRT for this one?
You have to use it twice.
Oh, okay, I see.
Really? You look, you don't know, you know the pressure, but you don't know the temperature.
Okay.
You know the volume, but we don't know the amount.
Okay.
Yeah, it's a good question. Yes, we don't. She's asking whether we can use the ideal gas law equation, but the thing is, we don't know the n. That's the reason. Good question. Okay, I'll move to the next one. If a sample of air occupies 500 milliliters at 273.15 Kelvin and 180 m. What is the volume at 85.0 degrees of Celsius and 560.2 used for okay, right. Now we are given the volume, we are given the temperature, we are given the pressure. And what is the volume at the new temperature? Look, the first temperature is given in Kelvin, but the second temperature is not given in Kelvin. It is given in degrees of Celsius. So you have to change it to Kelvin. And the pressure, look, pressure is given in TOW. The first condition, for the first condition, the pressure was given in ATM. So you have to use this you need to change these one of these units into ATM or into the TOW. Then you because we should apply the pressures in the same unit. So you can basically use the P1 V1 over T1 equals P2 V2 over T2 equation. And you are looking for the new volume. Okay? Questions? Okay. So I hope you will be able to do that because we have done similar examples. Right. Uh, this is a multiple choice question. I'll give you 1 minute. So try to get the answer for this question. What is the answer? Okay, what is the combined gas law equation? P1 V1 over T1 equals P2 V2 over T2. In order for the combined gas law to be used, what variable must be the same under both sets of conditions? Temperature. No, temperature doesn't have to be same. Pressure. No, pressure doesn't have to be same. Volume. No. P, V, and T. Pressure, volume, and temperature must all be constant. No, doesn't make sense then. The amount, yes. If we use these, if we need to use the combined gas law equation, then the amount of the gas should be a constant or must be same. Okay. Questions? Any questions? We'll move to the next problem. Right. Okay, now we have come to the Avogadro law equation. Okay, Avogadro gas law equation. If 3 volumes of H2 are reacted with 1 volume of N2, how many volumes of ammonia are produced? Okay, hint, write the chemical reaction. Now we are going to balance the reaction. 3 volumes, okay. Under Avogadro law equation, it says if the temperature and the pressure are constant, the volume is proportional to the amount. Okay. So if it is 3 volume, we can assume it as 3 moles. Okay. H2 gas reacts with 1 more volume of N2. So it can be related as 1 mole. And how many ammonia? Oh, now you are not given the chemical formula. You must know the chemical formula of ammonia. It is NH3. So now how you can balance this? Yes. How many moles of ammonia will be produced? Or how many volumes? 3, 1, and 2. Answer is 2. Questions?
So on a quiz for this problem, are you gonna have us also write down the equation?
Yeah, you need to write down the equation.
Okay, and for every equation, just make sure you balance it.
Yeah,
Okay.
yeah, because otherwise, if we don't balance this equation, there is no way that I would find the coefficient for ammonia. Okay.
Okay.
Yeah, because in order to get the correct coefficient for ammonia, I had to balance the chemical equation.
Okay.
Yeah. Always, before you do any calculation, please make sure check whether you have the balanced chemical equation. That's a good point. Right, I'll move to the next one then. N2 gas plus 3H2 gas gives 2NH3 gas. If 125 liters of H2 reacts with 50.0 liters of N2, what volume of NH3 can be expected? Okay. So now you need to balance this equation and keep that in mind. You have learned in the module not 6 yeah, module 6, the stoichiometric ratio and the limiting reagents, right? So let's write this equation. Limiting reagent, this is this is based on limiting reagent equation as well, law as well. 2NH3, right? So what is the stoichiometric ratio? 1 to 3 to 2, right? So, and it doesn't say anything about the temperature and the um, pressure. So I assume that the temperature and the pressure, sorry, and the pressure are constant. They kept constant throughout this reaction. Okay, right. So 125 liters of H2 is allowed to react with 50 ml, 50.0 liters of N2, right? If I use the 125 liters, okay, how much should I receive from the for the ammonia? Then I would divide this 125 by, okay, multiplied by the ratio 3 to 2. This is H2 and this is H2 and this is NH3. Then what would be the answer? I think you also do the math part. Then I would receive 83.3 liters. Okay. But let's start with the 50. Okay. Then 50.0 liters of N2 multiplied by, then take the relationship 2 to 1. Then I will get the 100.0 liters of NH3. But look, what is the limiting reagent here? Yes, the hydrogen. So the what volume of ammonia can be expected? Yes, the 83.3. Actually, N2 was in excess. The product was limited. The amount of product was limited by the amount of hydrogen given with this equation.
Why is it 2/1 and not 2/3 when you're working with the 50 liters?
2/1.
Yes.
Do you see any coefficient in front of the N2?
No.
So then that the coefficient means 1.
Okay.
Here it's, look, it's 1 for nitrogen, 3 for H2 and 2 for ammonia.
I see now. Thank you.
Okay, yeah. Good. Any other questions? Okay, yeah, those are good points because students do those mistakes a lot. And when you ask a question like this, it reminded everyone not to look at the same thing. Then they'll know, okay, how that 1 has come, how that 2 has come, like that. Okay, good questions. I'll move to the next one. how many liters of N2 gas at 1.00 atm and 25 degrees of Celsius are produced by the decomposition of 150 grams of sodium acid, so nitride. Okay. Um, this is acid. Yeah, sodium nitride. Okay, right. So how many liters of N2 at will be produced? Right. Okay, but first thing what we should do, we need to check whether we have the balanced chemical equation. Do we have the balanced chemical equation? Sodium 2, nitrogen 6, 3. Oh, good. Yes, we have that. Now, we are given only the 100.60 grams of the NaNa3. And we need to find the liters of this. Okay. So, first, okay, here we are going to use the ideal gas law equation. But before that, we need to find the moles of this N2. How we can find the moles of N2? Yes, we'll find the moles of N2 using the stoichiometric ratio of this uh, based on that. Okay, moles of N2 gas. So we'll start with the 150 point grams of sodium nitrite. Okay. Huh. What should we do first? We need to change that into the moles. Okay. Uh, I'll I don't have enough space here. I'll start from here. Moles of Na, sorry, N2. Right. So that would be the oops, moles of NaN3 times 3 moles of N2 divided by the 2 moles of NaN3. I got this relationship from the coefficients. Okay. 3 moles of N2 to 2 moles of NaNa3. Right. Now we need to find the moles of NaNa3. NaN3. Yes. What should we are given the mass, but we need the molar mass of this. Okay. Molecular weight of that. Can somebody find the molecular weight of sodium nitride? Sodium is 23. Okay. I'll just go with this. Okay.
It's
So you
65. It's
what?
65.011.
Okay. Thank you. 65.011.
11 grams over milliliter. Grams over mole.
Grams per moles. Okay. Thanks. Right. So we'll find the moles of NaN3. So that is we divide the grams of NaN3 by the molar mass 65.011 grams per mole. 3 moles of N2 divided by 2 moles of NaN3. Right. So grams to grams cancel out, moles to moles of NaN3 cancel out. We'll get the answer in the moles of N2. So what would be that? The 150 multiplied by 3 divided by 65.011, that would be 6.921. Okay, so since 302 we don't care about those things, but 150 point has 3 significant figures, so I can use the intermediate answers with one plus significant figure. Okay, so I can have the intermediate answer with 4 significant figures. So I'll use that as 6.922 moles of N2, right? Okay, now I know the moles of N2. Let me get another color. Oh. Mm. Okay, now I'm going to use, okay, now I have the pressure. Now I have the temperature, and we know the gas constant value, and I know the N. Now, can I find the volume in liters? Yes, because now I can use the ideal gas law equation, which is PV equals nRT. PV equals nRT. So V equals nRT divided by the P equals, okay, so you can plug all these numbers. Oops, moles of N, and now you can use the 0.08 the ideal gas constant with the ATM value. Okay, and remember to change this temperature to Kelvin, and you will get the answer in liters for this question. Do you guys have any questions?
I just got a different number for moles of N2. I got 3.46 when I plugged in to my calculator the exact same equation that you did.
What?
So for 150 over 65 times 3 over 2, I got...
Oh, okay. I may have. Thanks for the reminder. Didn't I divided it by? Oh, sorry. Thanks. Yeah, I didn't divided it by 2. Good point. Yes, you are correct. I got the 3.461. Thanks. Thanks for catching that. Yeah, I haven't divided it by 2. So here it's again that the 3.461. Any other questions or concerns or any mistakes? All right, let me go to the next question then. I have used the same equation here. Don't worry. Okay, then I'll move to the next. Dry ice is solid carbon dioxide. What is the pressure in ATM of CO2, carbon dioxide, in a are you guys with me? Hello?
You cut out for a second, but you're back now for me.
Yeah. Let me turn off my camera, then it would save some. Okay, yeah. All right. Yeah, we are back. Okay, so dry ice is solid carbon dioxide. What is the pressure of in atm of carbon dioxide? Okay, right. So we have the volume, we have the temperature, we have the mass, right? And now we need to find the pressure. Which equation that we must use? Yes, we need to use that. The PV equals nRT, right? So, but you would say, oh, I don't see the mass in this equation. Yes, you don't see that. But how we find the n, the amount? You divide the mass by its molecular weight. Okay, so we can plug that directly. PV equals N mass divided by the molecular weight RT. Okay, so we're looking for the pressure. So let's rearrange this. P equals mass over molecular weight R, T, and V. Okay, now let's plug all these values. Mass, it is 33.0 grams R. So since we are given the volume in liters, and then we can use that 0.082 liters atm, and per Kelvin gas constant, and the temperature. Now you need to change this 35 to Kelvin. What is the number then? 35 plus 273.15 308.15 Kelvin divided by the molecular weight of carbon dioxide is 44, I think, times the volume is 50.0 liters. Right, when you solve this, you will get the answer in atm, moles to here there will be moles in the answer. Moles to moles, Kelvin to Kelvin cancel out, liters to liters cancel out, and grams to grams cancel out, and you'll get the answer in atm. And how many significant figures we should keep in our answer?
3.
What?
3 significant figures?
3 significant figures? Okay. Yeah, that's right. And okay, do you have any questions? Okay, then I'll move to the next one. Since I have done a similar example, I'll skip it. Okay. You can use the same kind of equation, that the rearrangement I have used in the previous one. Okay, I'll do this one because it has used with the density. A gaseous compound of phosphorus and fluorine with an empirical formula of PF2 was found to have a density of 5.60 grams per liter at 23.0 degrees of Celsius and 75.750.2. Calculate its molecular mass and its molecular formula. This is a long question. Density. pressure and the temperature. And we are going to find the molecular mass and its molecular formula. So what equation we are going to use? Yes, the ideal gas law equation. PV equals nRT. But how we can rearrange to the density? Again, you will use the N as mass divided by the molecular weight. PV nRT. Okay, now I'm going to rearrange this. Mass divided by the volume, RT divided by the molecular weight. Okay, or the molecular mass. Right. I would say the MM. Okay, molecular mass. Right. M over V. What is M over V? Mass over volume. That is the density. Very good. So density dRT divided by the MM, molecular mass, and pressure. Okay, now you rearrange this molecule because you are going to find the molecular mass. dRT over P. Do we know the D? Yes, we are given that 5.60 grams per liters multiplied by the D, the R. Okay, now we are given this one in two, right? We are going to use that the 0.082 liters ATM per mole per Kelvin. Okay, and the temperature should be changed to Kelvin here. Okay, and divided by the pressure. Right, look, I applied the gas constant in ATM. So what should I do? Yes, I should change this pressure to ATM. How can I do that? 750 to 1 ATM. 1 ATM equals to 762. Okay, so I hope now you can get the relationship. 750 divided by 760, it is 0.98. So I have two significant figures actually there. I'll keep it with 3987. Okay, I hope you will be able to find the molecular mass. Right. So since we have done this type of example, like when we have the molecular mass and we know the empirical, when we are given the empirical formula, you should be able to find the molecular formula. You divide the mass of the, you divide the molecular mass by the mass of empirical formula and you will get a factor. And then you multiply that. As an example, okay. This is just an example, okay? Uh, uh, as an example, I assume that PF2, okay, this is just an example. PF2 is 25 and I got the molecular formula as 50. Then I divide the 50 by 25 and I get the factor as 2. Then what would be the molecular formula? Yes, then I multiply it by 2. So then it would be P2F4. Okay, this is just an example and not the answer for this question. Okay, since I do not have the correct the answer, I just did an example and I just wanted to demonstrate how you can get the molecular formula. You guys have any questions? Okay, let me move to the next one. This is again a question similar to the previous one. Next one. Methane burns with the following equation. Let's see whether it is balanced. Yes, it is balanced. And the combustion of 4.50 liters of methane, CH4, consumes how many liters of O2? Both volumes measured at standard temperature and pressures. Okay, that means the temperatures and pressures are kept constant throughout this experiment, right? Okay, so we can get the stoichiometric ratio, right? 4.50 liters of CH4, and we'll get the stoichiometric ratio. What is the stoichiometric ratio for the CH4? It is 1, and the O2, it is 2. So we'll get the 9.00 liters of oxygen. Right. Questions? Uh, let me see. I hope you will be able to do this one because we did a similar one. We started with the mass of another solid sample, and then we related it to the pressure of other one, like using the moles. Okay, first you need to find the, okay, uh, you in this equation, first you need to find the moles, okay, of carbon dioxide. Then you related it to the sodium carbonate, because when this is balanced equation, so you will have the same moles of carbon dioxide to the sodium carbonate, because they both have the coefficient of 1. Okay, right. So you will be able to find the moles of carbon dioxide using the PV equals nRT equation. N equals PV over RT. You have the volume, you have the pressure, you have the temperature. And using the gas constant, you will be able to find the N. Okay, that's how you will find the mass of the sodium carbonate. Here again, it would be the same thing. Okay. Okay, here. I just wanted to do this one. The Dalton's partial pressure law. Right. Okay. Mixtures of helium and oxygen are used in scuba diving tanks to help prevent the bends. For a particular dive, 46 liters of helium at 25 degrees of Celsius and 1 atm, and 20, okay, this is for helium, and 12 liters of oxygen at 25 degrees and 1 atm were pumped into a tank with a volume of 5.0 liters. Calculate the partial pressures of each gas and the total pressure in the tank at 25 degrees of Celsius. This is kind of, even though this has small numbers, this is a long equation. Okay, we are given the, this is for the I would say helium, and this is oxygen. Okay, what are the conditions of helium? 46 liters, 25 degrees of Celsius, and 1.0 atm. And in O2, what are the conditions? 12 liters, 25 degrees of Celsius, and 1.0 atm. Can I just say, okay, calculate the total pressure? Can I just add the 1 atm plus 1 atm is, and can I give it as 2 atm? No, that is wrong, right? So I have to find the N from the each case. Good? Right. Were pumped into a 5.0 liter tank. And these, both of these will be combined in a 5.0 liter tank. So what you should do, you need to find the, okay, and the pressure would be same, 25 degrees of Celsius. So you have to calculate the Neve pressure for helium and Neve pressure for O2. Okay, using the P1 V1 equals P2 V2. Okay, you have to do that for twice. P1 V1 equals P2 V2. So you can find the new pressures for the helium, and again you need to do that for the oxygen, right? And you will calculate the pressure of new pressure of helium and new pressure of O2. Those are the partial pressures, the partial pressure of helium and partial pressure of O2. Then you add those two pressures together to get the total pressure of the tank. Questions? I know I just explained it, but do not assume that you will be able to do this type of a question when you receive it for the quiz or for the final exam. Please practice it. Now I have shown you how to get the answer, but please do this. Next one. Uh, a mixture of 250 ml methane. Uh, again, this is again this is the same thing. What you have done the last time. Again, you need to do it twice and find the total pressure. Okay, here something that I am looking for. A mixture consists of 122 moles of N2, 137 moles of C3H8, and 212 moles of CO2. What is the mole fraction of each? How do you find the mole fraction? Yes, the mole fraction equals the moles of I. If I said the moles of I divided by the moles of total. Okay. So as an example, in this case, if I want to find the mole fraction of N2, then what is the moles of N2? It's in the numerator 122, and in the denominator I have to add all the moles of the each and every component. 122 from N2, 137 from C3H8, and 212 from carbon dioxide. Okay, so like that. If I want to find the mole fraction of C3H8, then I need to divide the 137 by 122 plus 137 plus 212. Okay, like that. You can find the mole fraction for each component when you know the moles of each component. Questions? I'm sorry, I'm taking some extra time. Right. Next one. The partial pressure of oxygen was observed to be 156 torr in air with a total pressure of 743 torr. Calculate the mole fraction of O2 present. Okay. So when you study the partial pressures, Dalton's partial pressure law, you will find this equation. The partial pressure of any individual component equals to the total pressure times the mole fraction. Okay. So now we are looking for the mole fraction. Mole fraction equals the partial pressure divided by the total pressure. The partial pressure of the oxygen is 156 to divided by the total atmospheric pressure, that is 743. So you can get the partial pressure. Questions? Let me move to the next one. I'll have done these things. Okay, so I hope. Okay, here, because this question is based on the Graham's effusion law. It says when the rate, okay, the rate will be effusion rate is increases when the gas is lighter. Okay, O rate is inversely proportional to the molecular mass. Okay, so the lighter gases can effuse rapidly than the heavy gases. So what is the order of increase in the rate of the effusion? So glad we are given the the molecular masses, right? So what is the lightest one? Yeah, the increasing rate. So H2 and then helium, then the neon, then the O2, then the argon. Okay, right. Because argon is the heaviest one, so it will have the slowest rate of effusion. Right. This is the, I think, the end of this. For a given sample of gas, under which conditions are actual pressures likely to deviate most from pressures calculated based on ideal gas law? Yes, the ideal gases. When we are doing the calculations, we assume all these real gases behave like an ideal gas. But the real gases have the molecular interactions, attractions and repulsions. Due to these molecular interactions, interacting forces, the pressure will be lowered because then the molecules will stay close and they don't go and hit with the walls. So then the pressure will be lowered. So when the attractions are strong, then the real gas will deviate most from the ideal gas conditions. Right. So strong attractions. Right. Next, when the temperature is high, the molecules will get higher kinetic energy. Okay. Then the molecules will move rapidly. Then they'll cross each other and they'll start to move randomly and rapidly, and they'll hit the walls a lot. Under higher temperatures, the real gases act more like the ideal gases, but at low temperatures they'll deviate most. And the larger volume and the small volumes. Okay, what would happen in a small volume? Yes, then the molecules are closer. Then they'll not go and hit with the walls of that thing. But when the volume is large, the interactions are getting weaker because then molecules are apart. So then they'll act more like the ideal gas law. So, oops, I'm sorry. Therefore, the strong interactive molecules reduce the pressure. Oops, I just cut my low volumes again. The make the real gases deviate from the ideal gas conditions. So under these conditions, so these effects lead to a lower actual pressures than those predicted ideal gas law. Okay. Strong interacting molecules, low temperatures, and small volumes. Yeah, the answer is E. So this is the end of this the practice session, and please email me if you have any questions.